Hello everyone, this is Charu Sharma this side, and today I will be teaching you physics chapter Gravitation, where we are going to deal in today's class with two topics, that is Kepler's law and Newton's laws of gravitation. Okay, so let's get started with the first law of Kepler. So Kepler was a scientist and he actually gave three laws with respect to how planets revolve around the sun. So he gave three laws. The first law was Kepler law of orbits. Kepler law of orbits. The second was Kepler law of areas, and the third one was Kepler law of time period. So these were the three laws given by Kepler: Kepler law of orbits, Kepler law of areas, and Kepler law of time periods. Now coming to the Kepler law of orbits, the first law, what does it states? The first law states that planets around the sun revolve in an elliptical orbit. So planets revolve around sun in an elliptical orbit. So what did he say in this law? That if you consider this is an ellipse, this is an elliptical orbit in which this planet is revolving. For example, this planet is revolving and this is your sun over here. So he stated that this planet is going to revolve this sun in an elliptical orbit, and sun is located at one of the focus. So if you know, the ellipse has two foci. This is foci A and this is foci B. So two focus it has. So sun will be at one of the focus for the planet, and we can say like this, this part we can call it as semi-major axis. Semi-major axis, and this part we can call it as semi-minor axis. So I'll be explaining you again by drawing a big figure. So he stated that planets will revolve around the sun in an elliptical orbit, and in that elliptical orbit the sun will be located at one of the focus, and we can see the semi-major axis and semi-minor axis, and then we can go to calculate eccentricity. So if I take, this is the ellipse, and here was your sun, and here is your planet. So this part I am denoting as A, and this part I am denoting as B. So here I say A is semi-major axis and B is semi-minor axis. Now sun is at one of the foci, so this is focus 1 and this would be the second focus, but here we do not locate sun. Sun will be only at one of the foci, and this is our planet. So this is our planet. Now we need to calculate one more thing. So the distance from the sun, suppose the planet is here. So when the sun is on this focus, if we consider, and the planet comes at this position, then this is supposed to be the maximum distance the planet can have with the sun. So this is known as R max. And when planet comes at this position, this is going to be the minimum distance with sun which a planet can have. Okay, so this is called as R min, R minimum, R maximum. And for the maximum part we call it as aphelion, and for this one we call it as perihelion. So for the maximum distance we will be calling it as aphelion, and for minimum distance we will be calling it as perihelion. Now there is a term called eccentricity which is calculated for these elliptical orbits. So how do you calculate that? Is E is equals to under root of 1 minus b square upon a square. So E is equals to 1 minus b square upon a square, where b is the semi minor axis and a is the semi major axis. This is the formula you need to remember for calculating eccentricity. And one more thing, as I said, this is the R max and this is the R min. So if you calculate A, what was A? A was semi major axis. The A you can state in the terms of R max and R min by this formula. Semi major axis is equal to maximum distance plus minimum distance divided by 2. It's simply the average of maximum and minimum distance. Okay. So the semi-major axis is the average of maximum and minimum distance. So these two formulas you need to remember. And one more thing, you can also find the relation between R max and R min. So R max is equal to semi-major axis into 1 plus E, and semi-major axis into 1 minus E will be your R minimum. Now you are thinking that where these all formulas will come to use. So let's move on to a question, and then you will come to know where these formulas are coming to be useful. Okay. So this is what I am going to repeat once again. So the first law of Kepler. What is that first law? Law of orbits, which states that the planet is revolving around the sun in an elliptical orbit, where sun is at one of the focus, and there is called semi-major axis and semi-minor axis, and the maximum distance the sun can have with the planet, this is called R maximum aphelion, and the minimum distance the planet can have with the sun is called R minimum or perihelion. And we calculate eccentricity here for the planets by this formula, which is under root 1 minus b square upon a square. And you can also say that semi-major axis is nothing but the average of R maximum and R minimum distance. And you can also relate R maximum, semi-major axis and eccentricity with this formula. So R maximum is equals to A into 1 plus E, and R minimum is equals to A into 1 minus E. So till now I have just taught you three formulas which are very important. This one, and this one. Just these three formulas you need to remember with regarding the first law of Kepler. So let's move on to one question. Then you will understand where are we and how are we supposed to use this formula. So I am giving you a question that semi-major axis, that is A, is given as 5 light years, and semi-minor axis is given as 3 light years, and in question they are asking you to calculate eccentricity. Then how are we supposed to do? Now we know the formula. That's very easy. E is equals to under root of 1 minus b square upon a square. So we go under root of 1 minus, what is b square? 3 into 3, which is 9, upon 25. So you will be getting this as 16 by 25, which is 4 by 5 is your eccentricity. Okay. In the same question, if I am asking you what is the ratio of R max, what is the ratio of R maximum distance upon R minimum distance, if I am asking you this ratio, then very easy. I already said you that R maximum upon R minimum, this is nothing but A into 1 plus E, and this is A into 1 minus E. So when you solve this, A gets cancelled. 1 plus E is 4 by 5, you got 1 plus 4 by 5 divided by 1 minus 4 by 5. So this will be 9 by 5 upon 1 by 5. So your answer comes to be 9 by 1. So the ratio of R maximum to R minimum is 9 by 1. So like this they will ask, they will give you major axis distance and minimum axis distance, and they will ask you to find the R max and R minimum values. So like this you can use this formula for the first law of Kepler. Now coming to the second law, which was law of orbits. This laws come from law of conservation of angular momentum. So here what it states that second law, law of areas. So this comes from conservation of angular momentum. Okay, so law of areas, it says that suppose this was your elliptical orbit, right? So here was your sun at one of the focus. Now the planet is coming from this point to this point. Let us consider A to B. So if I calculate this area by meeting the sun, this area, let me call this as area 1, and I gave to cover from point A to B, the area was covered as this is your sun. Okay, so the area which was covered in time t, okay, this area 1 was covered in time t. Now similarly, if planet from here to here, if it comes from C point to D point, and again it sweeps an area called A2, but I am keeping the time same, I am keeping time t only, then what will you observe? That area 1 is equal to area 2. That means that planet will sweep equal area in equal time. So this is the statement which you need to remember for law of areas, conservation of angular momentum. Now how angular momentum is conserved? Let's see. So this, I hope you got this. Now as we are saying that same area is covered in same time, that means nothing but angular momentum is conserved. The angular momentum is not changing. What is angular momentum? Angular momentum, which we denote by L, is nothing but product of momentum into the perpendicular distance. So that is, momentum is mass into velocity into r. Mass into velocity into r is angular momentum. So if I say this was your elliptical orbit, like this, we have taken two areas A1 and A2. Suppose planet is having mass m, and it is covering from here to here with a speed v1, and from here to here with a speed v2, and distance, of course we know, this is the maximum distance r max, and this is the minimum distance r min. Okay, so you need to apply common sense that when the planet is far from when the distance is maximum, velocity is going to be minimum. That is what nothing but angular momentum says that, because this product of mvr must be constant. Now as mass is constant and r is increasing, what should decrease to keep the whole ratio same? Velocity should decrease. I hope you got it. So if you see in the terms of formula, it says that m1 v1 r1 is equals to m2 v2 r2. I will explain again. See, law of area says that it's conservation of angular momentum. It says that in same time the same amount of area is conserved. Now if I am taking this m1 v1 r1, mass of the planet is going to be same. If I take here mass, both are going to be same and gets cancelled each. So v1 r1 is equals to v2 r2. Now instead of taking r1 r2, what I am doing is, you know that from this sun to this planet, this distance is maximum and this distance is minimum. So I am taking this as r max and I am taking this one as r minimum. Okay, so this will be r maximum and this side I will be taking as r minimum. Okay. Now you tell me that you need to make this both equations equal. Now if here radius is getting maximum, velocity should get minimum, right? That's why when the planet is at the far distance from the sun, velocity will get minimum. That is v min we write this side and v max we write that side with r min. Because here distance is minimum, velocity will get maximum to conserve the angular momentum. I hope you understand this. So you just need to remember that angular momentum gets conserved, that is m1 v1 r1 is equals to m2 v2 r2. Okay, so that wherever your radius is getting maximum, your velocity is getting minimum. Okay, like this. I hope you got that. So this formula you need to remember, that r max by r min is equals to v max by v min, or you can just calculate from angular of conservation of angular momentum, that m1 v1 r1 is equals to m2 v2 r2. And also for this laws of area you need to consider that equal amount of areas in equal amount of time is equals to L by 2m, and this is equals to constant. That's what we said now, that equal amount of area and equal amount of time will be always constant according to law of areas with respect to Kepler, and this is equals to L by 2m. So I hope. So the third law of Kepler is law of time periods, which states that square of the time is directly proportional to cube of the distance. So if suppose this was your ellipse and here is your sun and here is your planet, and this is the distance between the sun and the planet. So this distance we consider as r, and the time it takes to complete one revolution we will consider as t. So this will be your equation, t to the power 2 is directly proportional to r to the power 3. The square of time periods is directly proportional to cube of the distance between the planet and the sun. Now let's move on to the second part of the class, which was, like I said you, today's class will be having two topics, Kepler's law and Newton's law of gravitation. So we are done with the Kepler's law. What were the three laws? Let's get revision. So the first law was about orbits, that always the planet revolve in the elliptical orbit, and we came to know about eccentricity of this formula, and we came to know about r max and r min relations with semi-major axis, that is 1 plus a into 1 plus a, and this is a into 1. This is sometimes directly asked in question, that what is the ratio of r max by r min, and directly in the options you will see 1 plus e divided by 1 minus e. And the second was law of areas, where we said that it is conservation of angular momentum, m1 v1 r1 is equals to m2 v2 r2, and equal areas to obtain equal time is equals to L by 2m, which is a constant value. And the third was law of time periods, which is derived from Newton's law of motion, Newton's law of gravitation, which is t square is directly proportional to r to the power 3. So these were the three laws given by dear scientist Kepler. Now let's move on to the second part of the class, which is universal law of gravitation, nothing but given by Newton. Universal law of gravitation. This was given by whom? Our dear scientist Newton. So what does that state? We have also read in junior classes like 8 and 9. We already dealt with it. So this considers the point masses. It talks about point masses, and it can also be applied to spherical bodies. If there is any disturbance, audio, please ignore that. Point masses and spherical bodies. So what does that state? That if you are having 2 point masses, that is of mass m1 and m2, and the distance between them is r, so the force of attraction, and always remember this gravitation is always force of attraction, it's never repulsion, okay? So you will always consider it to be force of attraction only. So attractive force only means positive forces only. These are not negative forces. So these were two bodies. This is having mass m1 and this is having mass m2 and the distance between them is r. Then the force applied on one mass by the other will be directly proportional to the product. The forces between them is directly proportional to the product of masses and divided by the and inversely proportional to square of the distance between them. So this is nothing but given by universal law of gravitation given by Newton. And if you want to remove the proportionality sign, you use a constant called universal gravitation constant called G, m1 m2 upon r square. Now what is the value of G? It is universally given 6.67 into 10 to the power minus 11 Newton meter square upon kg square. Okay. Now this was a general introduction to Newton's law of gravitation. And also, now let's see how do we calculate. Sometimes in the question, they will ask you to calculate dimension of G, universal gravitation constant. For this G, they will ask you to calculate the dimension. So how do we calculate dimensions? F is equals to G into M1 into M2 upon R square. Now what is force? Force you can write as M L T to the power minus 2. How did I get this dimension for force? From this equation, F is equals to ma. A is acceleration, m is mass. So acceleration can be written as velocity by time, and velocity can be written as distance by time. So t square it becomes. So from here you get these dimensions for the force. Okay, and this is equals to G, and these are masses, so I can write m square directly, and for this I can write L square. So how you will get that? M to the power minus 1, L to the power 3, T to the power minus 2 will be the dimension for G, gravitational constant. Okay. Now, also one more point, sometimes in type of theory questions if they want to ask, they can ask, suppose this is your spherical shell. If I am telling this is a spherical shell, this is a spherical shell. Now what does you mean by shell or spherical shell? It's nothing but hollow sphere. Means there is no mass inside. Okay, there is no mass inside. So if I say that if you place a mass over here, now there was actually no mass air filled over here, but now I am placing a mass m over here. So on this mass there will be no force active. No force active due to gravitation. Due to gravitation. So if you keep a mass inside a spherical shell, there will be no force acting due to gravitation. Why is it so? You know, suppose if I am taking this part of the shell, this shell means outer side, the whole mass is distributed to the outer corners. Suppose I am taking only this much section of this shell and this much section. Suppose this is having mass m1 and similarly this is also of equal mass m1. These two opposite sections I take, and now this mass will be applying some gravitation force on this mass towards this side because that is attractive force, and similarly this mass of same equal m1 will be applying gravitation attractive force this towards this side on this small mass m. So if you see, as both the masses are equal and I am considering distances are also equal, then these both forces are equal and gets cancelled. So like that, so many infinite sections can be taken on this shell, and hence there will be no net force on this mass which you kept inside a spherical shell. So you need to remember that no force acting due to gravitation when a mass kept in spherical shell. Okay, there will be no force. If I keep a mass here also, suppose like this M2, like this mass I am keeping, then probably there may be some force. But due to the shell, I am talking here due to the shell there will be no force acting on this inner mass. Okay, like how we will study in electricity, electrostatic shielding, just like that. Okay, so we are done with all the introductory part. Now let's derive. I said we will derive this. So let's derive that equation, and then we are going to do one interesting question also. See, we know that the sun was here and the planets were revolving around it like this. So for revolving this planet, they required some force. And from where does that force come? It will obviously come through the centripetal force, right? Centripetal force. Because of that centripetal force only the planets are going to revolve. Now the centripetal force will be equal to the gravitational force, because centripetal force is nothing a new force, it is just a net force, net centripetal force. It's something, it comes due to reason of some another force. It's not naturally present, like how gravitational force is naturally present, centripetal force is not naturally present. So centripetal force will come from due to some other force. So this centripetal force is nothing but the gravitational force between the planets, or between the spherical bodies, that is sun and the earth over here. So centripetal force is equal to gravitational force. So now what is I can say required centripetal force. No? Required centripetal force is equals to the gravitational force between the planetary bodies. Now centripetal force I can write as mass of the planet, I am taking m, and mass of the sun I am taking capital M. So mass of the planet into mv square, velocity, it's revolving with the velocity v, and this distance is r, radius r, that is equals to gravitational force. And now only we learned how to take gravitational force. So you will see that mm gets cancelled, so r also gets cancelled. V is equals to under root of gm upon r. So from here you got a equation for velocity. Now you also know that time period is equals to distance upon velocity. Time period is equals to distance upon velocity. Now what is the distance? This is the circumference. The circumference will be 2 pi r, and velocity you need to take this whatever we got here. So that is equals to under root gm over here and under root r over here. So when you solve that, you are going to get t is equal to 2 pi under root gm to the power r 3 by 2. So you know this I am taking as I will take this r inside the square as I will take a square, so it will become cube, and then I will remove this root, so it will be under root 2. So it will be, so you will get time is equals to 2 pi under root gm and r to the power 3 by 2. So from here you can say time is directly proportional to r to the power 3 by 2, or time to the time square is directly proportional to r cube. So what was the proportionality constant? Sometimes this may be the question, that when you are taking this equation, what is the proportionality constant if they ask you? That will be proportionality constant, this 2 pi by under root gm. This will be proportionality constant, or you can say if you take the root inside, it will be 4 pi square under root gm. So this will be the proportionality constant. So this is actually how we derive this. We derive from centripetal force, gravitational force, we take mv square by r, then gravitational force, then we find velocity, then we put it in the equation time is equals to distance by velocity. Distance is 2 pi r and velocity we found from this equation. then time period is equal to 2 pi under root gm r to the power 3 by 2. Then you get this equation. From here you can get the proportionality equation, or also you can get the proportionality constant. Now this was general. This is like general application. In all questions you will be applying this. Suppose if a question is asked. Now here if you see that force was inversely proportional to r square, right? From this equation, force was inversely proportional to r square. So time period was directly proportional to r to the power 3 by 2. So there must be some relation between force and time if they ask. Then how are we supposed to find? So if a question is asked that if force is inversely proportional to r to the power n, instead of r to the force was inversely proportional to r square, instead of square I am putting n, some integer. Force is inversely proportional to some integer here. Then time is proportional to r to the power question mark. If they are asking you to find this, then how you will do? Similarly, mv square upon r, centripetal force, is equals to gravitational force. But here just what you need to remember, instead of r square you need to write r to the power n, because it is given in the question. So again you will find a equation for velocity. So for velocity it will be coming as v is equals to under root gm upon r to the power, it will come here, this will go and this will come up. So r by n minus 1 by 2. Now you got the equation for velocity. Just 2. So when you will put this velocity equation over here, you will get r is equals to 1 plus n minus 1 by 2. So time period is directly proportional to r to the power n plus 1 by 2. So this will be your equation. So suppose if they are giving you force is inversely proportional to r to the power 7, then what is time proportional to r to the power question mark? Just you not need to derive everything. Keep this formula, remember with you. So time period will be directly proportional to r. N was 7. So 7 plus 1 is 8. 8 by 2. So time is directly proportional to r to the power 4. So like that the questions will be asked here. So today's class we are done. We have done about Kepler's law, and we are also done about Newton's law of gravitation, and one application we did. So for that's it today's class. Now some homework I would like to give. Always I used to also follow. The homework is, now you need to give a NCERT reading. You need to give a NCERT reading. If there is any background sound, please neglect. You need to give a NCERT reading for Kepler law and Newton's law of gravitation. For these two things you need to give a NCERT reading. Okay. For these two things you need to give NCERT readings. Then you need to solve NCERT examples, whatever is given in the textbook, NCERT examples and backside exercises. Whatever the after chapter they will give some exercises, no? That backside exercises you need to solve, which are related to Kepler's law and Newton's law of gravitation. Around you will get around 6 to 7 sums over here only. And then if you have any module with you, any question bank or something like that, wherever you have your coaching modules, whatever you have a question, or you can download some PDF from net. Around 15 to 20 questions, get some questions on Kepler's law and Newton's law of gravitation, just 15 to 20 questions and 6 to 7 over here. Hardly 30 questions I request you to practice on Kepler's law and Newton's law of gravitation. Till then, bye bye. Practice this for today's class. Watch the lesson again if you are feeling confused, and I will be getting you the notes, so you can just go through the notes and then you can see the NCERT reading, and then you can go with NCERT examples and backside exercises, then do some 15 to 20 questions, and that's it, your job. And if you practice like that, I am sure that your score will boost up. And thank you for watching and putting your valuable time here. Thank you for watching this video. I am very grateful to you. Thank you very much. Please do like, share and subscribe the channel.